Hello everyone, my name is Michaela Relford and I am a second-year mechanical engineering major at the Georgia Institute of Technology, or Georgia Tech. Today, I'm going to be discussing Lab 4 for my Physics 2212 class, which uses conservation of energy and current conservation to predict behavior of circuits, measures conventional current, and examines behavior of ohmic resistors and capacitors. For this lab, we used a Java applet in order to simulate an ideal circuit. Some important concepts that we used in this lab are Ohm's law, the loop rule, and charge conservation, which worked with the equations appearing on screen now. For the first part of the experiment, we set up a series circuit in the fashion of the image on screen. We used two 1.5 volt batteries, a 47 ohm resistor, and a 100 ohm resistor. We used two ammeters to measure the current I of the circuit. The predicted value for the current that we calculated was 0.024 amps, and the ammeter on screen measured the current in both locations before and after the resistors to be 0.02 amps. This reading stays the same when we reverse the direction of the ammeters. When we replace one of the ammeters with a voltmeter, we can see that the potential difference is 3 volts, and the ammeter now reads 0 amps. The reading on the ammeter tells us that the current is no longer moving. The potential difference would be 0 in a closed circuit. Once we close the circuit, we measured the potential difference at various locations of the circuit. There are a couple of important things to take note of here. First, the potential difference from location G to location H is 0, which means that the ammeter does not cause any resistance. We know that we are working with an ideal ammeter because a real ammeter would cause some resistance in the circuit. Second, when we sum together all of the individual potential differences measured in the circuit, we can see that the net potential difference equals 0. Thus, we can conclude that the potential difference of one round trip for a circuit equals 0. For the next part of the experiment, we placed an ammeter in parallel to the 100 ohm resistor. The current, and therefore the reading, changed due to a new path in parallel, providing a path for the current with lower resistance. Using the data we collected, we were able to calculate the resistance for each of the circuit elements. We found that the first resistor was 47.95 ohms, the second resistor was 102.05 ohms, and both the wire and ammeter were 0 ohms. For this next part of the experiment, we set up a circuit with one 9-volt battery, one light bulb, and one 0.2 Faraday capacitor in series, and we timed how long it took to charge and discharge the capacitor. First, we set up the circuit such that it was powered by a battery, and the light from the light bulb slowly became dimmer as the capacitor charged. Then, we disconnected the battery and used the capacitor as a power source. Again, the light became dimmer as the capacitor discharged. For a 10 ohm light bulb, we found that it took 3.33 seconds for the capacitor to charge and 4.35 seconds for the capacitor to discharge. For a 20 ohm light bulb, it took 9.38 seconds for the capacitor to charge and 21.82 seconds for the capacitor to discharge. Using a similar setup with a 30 ohm light bulb, we recorded 20 seconds worth of data and plotted the natural log of the potential difference divided by the initial potential difference versus time t. The slope of this graph can be used to calculate the time constant Rc, which we found to be 1.91. In conclusion, we used the principles of Ohm's law, the loop rule, and charge conservation to determine a few things. We demonstrated that the sum of all of the potential difference of one round trip around a circuit equals 0. We also found that charge will find the fastest way to move through a circuit, and we found that it was important to note that the data recorded here from ideal materials would differ from a real-world experiment. And we found that a capacitor takes longer to discharge than it takes to charge. Thank you.